Hello APC Mechanics students, today we'll solve the past paper FRQ 2008 exercise 2. The horizontal uniform rod shown above has a length 0.60 meters and mass 2.0 kg. Now uniform rod, it means that the mass is distributed uniformly and the center of mass is the geometrical center of the rod itself. The left end of the rod is attached to a vertical support by a frictionless hinge that allows the rod to swing up or down. So here we have a hinge. Now it is frictionless. The right end of the rod is supported by a cord that makes an angle 30 degrees with the rod. A spring scale of negligible mass measures the tension in the cord. So what is the role of the spring scale? Is to measure the tension in this cord. A 0.50 kg block is also attached to the rod at the end of the rod. On the diagram below, draw and label vectors to represent all the forces acting on the rod. Show each force vector originating at its point of application. Now, first of all, because the rod has a mass, then it will be subjected to the pull of gravity at the center of the rod. So here we have the pull of gravity. Now let me denote the mass of the rod to be capital M, so that would be mg. Now here we have the tension provided at this point due to this mass, and let me say this is a small m, so here we have also mg. And notice that I have represented it smaller in length because 0.5 is less than 2, so this is mg, although in the question itself they didn't state to take the relative length of the vectors itself into consideration. Now we have the tension along the string, which is like that. And finally, although the hinge here is frictionless, but we know that we have a reaction. Now what about the direction of this reaction? Now notice that the tension has a left component and all of these are down, so the reaction should be represented like that, having a right component, because we know that the system is at equilibrium. Now in part B, they're asking us to calculate the reading on the spring scale, so which means that we need to determine the tension, because remember that the tension the spring scales the scale read the tension. Now one way to do it is using equilibrium condition for translational motion, but notice that if we're gonna use balance forces left, right, up and down, we don't know the reaction at the hinge itself. Then the way to proceed in this exercise is using rotational equilibrium. Then let me say that the net torque equals to 0, and this is because of the rotational equilibrium. And now we're gonna apply it about which point. We're gonna apply it simply at this point, because in order to eliminate the torque produced by the reaction. Then here we have the torque produced by the reaction, the torque produced by the pull of gravity mg, let me say capital M, plus the torque produced by the small m, plus the torque produced by the tension, equals to 0. And let me consider the anti-clockwise direction to be positive. Now the length of the rod is 0.6 meters. Then basically this distance would be 0.3 and this distance would be 0.6. Now directly we can eliminate the torque produced at the hinge or at the reaction, so 0 plus. Now notice that these two forces are being applied tangentially, so no need to consider cosine or sine, and they are producing torque in the negative direction, so that would be mg multiplied by L over 2, which is the length of the rod, plus, it would be minus then 0 minus mg L plus the torque provided by the tension. Now here we need to take into consideration the cosine. So let me say, and the distance is given by L, and now we need to add either cosine or sine. Now if you notice carefully, the angle here is given by 30 degrees. Now that's the radial direction, and that's the tangential direction. So if this is 30, then that would be 60. So the projection of the tension along the tangential direction would be cosine 60. And notice that I didn't add anything on our rigid body diagram. So that would be cosine 60 equals to 0. Now we can eliminate L, and T cosine 60 would be given by mg over 2 plus mg, and we're interested in determining the tension. So the tension in this case would be given by mg over 2 plus mg divided by cosine 60, which is basically equal to, now the capital mass is given by 2. Let me double check. Yes, that's the capital mass. Then 2 multiplied by 9.81. Remember, in a free response, it's better to use G to be 9.81 divided by 2 plus the mass, which is 0.5 multiplied by 9.81 over cosine 60. Now plugging that fraction on the calculator, we're gonna have that the tension, it's almost given by 29.4 newtons. Then the reading of the spring scale would be 29.4 newtons. Alright, now for part C, they're telling us the rotational inertia of a rod about its center is given by 1 over 12 ml square, where m is the mass of the rod and L is its length. Calculate the rotational inertia of the rod block system about the hinge. Now here, this is very important and we should be careful because they're telling us the rod block system. So we need to determine the rotational inertia about the hinge for a composite system consisting of the rod and this block. Now starting with the rod, we know it's given that the moment of inertia around this point is given by 1 over 12 ml square, and we're interested in determining the rotational inertia of the rod around the hinge, and this can be done using the parallel axis theorem. However, if you notice carefully, they're asking us for the rod block system. Okay, rod is done via the parallel axis theorem. Now what about the block? The block can be considered a particle, and the moment of inertia of a particle is given by ml square, in which L represents the distance from the particle itself, which is basically the block, considering that this dimension is negligible, to the center of the axis of rotation, or the rod, or the hinge, sorry. So first let's determine for the rod using the parallel axis theorem, then apply parallel axis theorem. Then I of the rod is given by I, the center of mass, plus the mass, which is capital M. And notice that this is a general formula for different quantities. I have used the length L to be small l. Let me use the same notation. Now we're adding a mass term compensating for the shifting in the axes, which is given by L over 2. So let me here say L over 2 to the power 2. Then I of the rod is given by I around the center of mass, which is 1 over 12 ml square plus 1 over 4 ml square, and that would be 1 over 12 plus 1 over 4 ml square. Now adding these two fractions together, we're gonna have 1 over 3 ml square. Now this is the moment of inertia only for the rod. Now for the block, let me say I of the block, that would be simply the mass of the block, which is small m, times the distance from the hinge to the block itself, which is complete L, then L square. And in this case, we know that the moment of inertia or the rotational inertia is an added quantity. Then I of the system would be I of the rod plus IB, which means that 1/3 ml square plus ml square, and that would be 1/3. The capital mass is 2. L is given by 0.6 to the power of 2 plus small m 0.5 multiplied by 0.6 to the power of 2. And plugging that expression on the calculator, we're gonna get that the rotational inertia for the system consisting of the rod and the block is given by 0.42 kilogram meter square. Now in part D, if the cord that supports the rod is cut near the end of the rod, calculate the initial angular acceleration of the rod block system about the hinge. So basically they're telling us that they're gonna cut this rod and we need to determine the initial angular acceleration, and this is very important, alpha I, the initial angular acceleration. Now why they're specifying the initial? Because if we cut the rod partly, you can assume that this will perform something like oscillations, and we know that in this case oscillations have an acceleration which is not constant. So for this reason they're specifying the initial angular acceleration, and we know that because we're talking about interactions, this can be done using Newton's second law for rotation. So let me say apply Newton's second law for rotation, and remember that in this case we need to specify our pivot point. So let me say about the hinge. Now torque net would be I alpha. Now what are the different forces that we have? We have the torque produced by the reaction, and that would be 0, plus the torque produced by the capital mass plus the torque produced by the small mass is equal to I alpha. And here notice that I didn't include the tension because it has been cut, so the string loses tension. Now let me consider the positive direction to be the direction of motion of the rod, which is like that. And here, if you're thinking about in part B why I have considered the positive direction to be anti-clockwise, that's not important because we are in rotational equilibrium, so the minuses will cancel in either case, the additional minus sign that you're thinking about. Now both forces provided by the masses are being applied tangentially, so that would be capital M, so 0 plus capital mg, which is the force produced by the capital M, multiplied by L/2 because it's at the center of mass, plus small m g multiplied by L. And that would be equal to the rotational inertia multiplied by I. And notice that because we're working about the hinge, this rotational inertia should represent the system rod block that we have determined previously, and it's about the hinge, so everything is in agreement. Now we're interested in determining alpha, so alpha in this case would be given by mgl divided by 2 plus mgl divided by alpha. Now we have all the numerics. Capital M is given by 2, G is 9.81, and L is 0.6 divided by 2, plus small mass, which is 0.5, G is 9.81 multiplied by 0.6 divided by the rotational inertia that we have determined, which is 0.42. And plugging that on the calculator, we're gonna have a value for alpha, which is the angular acceleration, given by 21. And remember that the unit of alpha is given by radians per second square. And that's it for me in this video, guys. See you soon in a new one.